Hello students, welcome to the next screencast. Today we're going to talk more about the counting principle that we started talking about in class. You might remember the counting principle. It's very, very handy, saves you some time so you don't have to list out all the possibilities when you want to know how many possibilities there are. So, let's begin. It's used in a variety of situations. So for this screencast, I'm going to present to you a variety of situations and show you how the counting principle can solve every single one. And then I'm going to present to you your problem to solve, and you will use the counting principle for it using the very same techniques you see me use now. Here we go. Here's the first one. A menu has 3 choices for salad, 5 main dishes, 4 desserts. How many different meals are possible if you select a salad, a main dish, and a dessert? In other words, how many different combinations can you have? Well, we saw that the counting principle states that if you have a certain number of choices for your first item, and a second number of choices for your second item, and another third number of choices for your third item, and a fourth number of choices for, and so on and so on and so on, all you need to do is multiply the number of choices for each to know the total number of possibilities. So, I have 3 choices for salad, I have 5 main dishes, and I have 4 desserts. So in other words, the numbers here that are important to me are 3, 5, and 4. Okay, so if I have 3 choices for salad, 5 main dishes, and 4 desserts, if I would like to know how many different meals are possible if I select a salad, a main dish, and a dessert, I have to take 3, 5, and 4, and all I need to do is multiply each of them. 3 times 5 times 4. Of course, if you do the math, is equal to, that's right, 60. So there are 60 meals possible if I have a choice of 3 salads, 5 main dishes, and 4 desserts. 60 meals possible. So that's a good beginning kind of introduction once again into the counting principle. Let's keep going. Now I'm planning a trip, and I can go to Phoenix, Las Vegas, San Diego, or Los Angeles. Tough choice. Do I go to Phoenix, Las Vegas, San Diego, or LA? Yeah, I agree. Vegas, let's go there. Anyways, you can fly or you can drive. From Chicago? Ooh, I don't know. And you can stay for 3, 4, or 5 days. How many possible trips are there? Alright, so let's think about this. First, let's talk about the cities. How many different cities do I have to choose from? I've got Phoenix, Las Vegas, San Diego, or Los Angeles, also known as LA. Alright, well that of course is 4 cities to choose from. Then I can either fly or drive, so therefore my mode of transportation, I have 2 options there. I can fly or drive. And then this last part, be careful. This one can be tricky. You can stay for 3, 4, or 5 days. Now I'm not going to multiply by 3, 4, and 5 altogether. No. What I have are 3 different options for how long I can stay in these cities. So, I could stay for 3, 4, or 5 days, which means I have a choice of 3 different amounts of time. So I just have to multiply 4 times 2 times 3. Alright, well what is 4 times 2 times 3? That's right, it's 24. So therefore I have 24 trips possible. Now notice once again, especially with this last part, this 3, 4, or 5 is kind of misleading. You might think, oh, I multiply 4 times 2 times 3 times 4 times 5. No. The 3, 4, or 5 days is telling you the options you have for the amount of days that you could, in fact, possibly stay in those cities, which means I only have 3 choices. So therefore I had to multiply by 3. Alright, good. Let's keep going. Now this one has to do with a lot more numbers. The telephone extensions at a company use 4 digits. You guys know what an extension is. It's how you get to a person's office once you've dialed the main number. If you'd like to call this person, please dial their extension. And one of those things. So part A, how many extensions are possible if there are no restrictions? And by no restrictions, they mean you can repeat certain numbers and you're not limited to only certain digits. In other words, if an extension must be comprised of 4 digits, this is the best way I recommend that you handle these types of password or code or extension type problems. Actually draw a line that represents each slot, each entry into the extension. So what I've done here is this will be the first digit, this will be the second digit, this will be the third, and this will be the fourth. Each one of these lines represent what number it could possibly be. In other words, a press of the keypad. This line represents a press of the keypad. This line represents a press. This line represents a pressing of one key on the pad. So how many extensions are possible if there are no restrictions? Okay, once again, I need to reiterate something that we talked about in class. How many digits are there? That's right, there are only 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. There are 10 digits. But Mr. Ripes, that's 0 to 9. Shouldn't that be 9? No, 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 no. 0 is the first digit. 1 is the second digit. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 digits. It's 10 digits because we are including 0. Now keep in mind, there are an infinite number of numbers. This is true. But every single one of those numbers, no matter how big, no matter how small, no matter how decimally, no matter how fraction-y, no matter how weird it is, every single number is composed of a combination of these 10 digits. So please understand there are only 10 digits, and they make up all the numbers. Knowing this, how many extensions are possible if there are no restrictions? Meaning we can repeat any numbers that we want. Heck, if we wanted our extension to be 1, 1, 1, 1, no problem. If we wanted to be 5, 6, 5, 6, we could. No restrictions whatsoever. So, in the first slot, in the first touch of the keypad, I have a possibility of 10 different digits. And because I can repeat them, I also have 10 different digits that I can choose for my second number. And I have 10 different digits that I can choose for my third and my fourth number. And the counting principle tells me that I need to multiply all of these together. All right, so what is 10 times 10 times 10 times 10? Well, yes, that is 10 to the fourth power, which we know is 10,000. So my extensions, how many extensions are possible if there are no restrictions? I could have 10,000 different extensions. Which leads us to part B. For part B, look at this one. Change the rules up a little bit. How many extensions are possible if the first digit cannot be 0 or 9? Interesting. All right, so what we have to do is consider, again, 1, 2, 3, 4 different digits that, of course, we're going to multiply together to find how many extensions are possible if the first digit cannot be 0 or 9. So once again, look down here. We have 10 digits, but we have to cross out a 0 or a 9. So therefore, the first digit, and the first digit only, it doesn't say all the rest, it just says the first digit cannot be 0 or 9, so therefore how many digits do we have to choose from? Well, we had 10 and we took away 2, so now we only have 8. But then it says only the first digit cannot be 0 or 9, which means the other 3 digits can be 0 or 9, or heck, any of the other digits as well. In other words, back to having no restrictions. So we take 8 times 10 times 10 times 10, and we figure out that this is nothing more than 8 times 10 to the third power, and if you do the math, you'll see that that's 8 times 1,000, and so you're talking about 8,000 different extensions you can have. And that's part B. Now, part C is very interesting. How many extensions are possible if the first digit can only be 1? So now we're back to being restricted for that first digit. So here these blanks represent the 4 digits that I want to enter. But now, once again, only the first digit can only be 1. So in other words, not 2, not 3, not 4, not 5, not 6, not 7, not 8, not 9, or not 0 again. So how many choices do we have for the first digit? We only have 1, and that just happens to be the number 1 itself. Now, what about the other 3 digits? Well, it doesn't give us any restriction on that, so we could choose any of the 10 digits once again for the other 3. And, of course, we are multiplying all of these together. So we do our math, and we realize this is 1 times 10 to the third power. And remember, 10 to the third power is 1,000, so 1 times 1,000, now you have only 1,000 extensions. So you see, by giving restrictions to your passwords, what you're really doing, or your extensions in this case, what you're doing is you're limiting the number of extensions that you could have. Now, don't get me wrong, this is probably a telephone company that's going to use a lot, or excuse me, it's a business that uses telephone. They're going to have probably a lot of employees. Will they have over 1,000? Well, if they do, then they probably should not restrict the first number to be just one particular digit. Anyways, let's move on to the next. Now this one is interesting. This one's about choosing a computer password. And we had a very large conversation today about why you need to diversify your password. And we saw that the more diverse your password is with different numbers, letters, uppercase and or lowercase, and even all those crazy characters on the keyboard like a star or an ampersand or a percent sign, or even the dollar sign or the pound sign, which we know now as the hashtag sign, or the question mark. You're diversifying your password. There are more options that it could possibly be. So here we have, you're choosing a computer password. The password has to be 3 letters followed by 3 digits. So it's 6 characters long. 3 letters and then 3 digits. Part A, how many passwords are possible if the letters must be uppercase? Okay, very interesting. Now, notice what I've done here. This really helps me. I have written 6 different slots, different blank lines, each representing a different character of my password. And below it, I've labeled what each slot must be. The first 3 must be letters, which I abbreviated with ABC, because when I see ABC, I think letters. And the last 3 must be digits. And I put a little pound sign here, also known as the number sign, to represent that it has to be a number. And I've done it for both A and B. So I remind myself that the first 3 letters must be letters, and the last 3 must be numbers. So part A, how many passwords are possible if the letters must be uppercase? Okay, well, we know there are 26 letters in the alphabet. Do not forget that there are 26 letters in the alphabet. You know who you are that need to remember that. Hint, hint. 26 letters in the alphabet. So therefore, how many possibilities do I have for the first letter of my password? That's right, I have 26. Now keep in mind, they are only uppercase. So we're talking about 26 uppercase different options. And because there's no restrictions here, in other words, I could have capital A, capital A, capital A, that means I also have another 26 to choose from for my second letter and another 26 to choose from for my third letter. But now, the last 3 characters can be digits. And as we saw before, I've got 10 digits to choose from, another 10 digits, and then a third set of 10 digits. So I have to multiply 326 by 3 tens. In other words, this is nothing more than 26 to the third power multiplied by 10 to the third power. Now, you might be surprised to know this, and I've done the math for you in the interest of time. But if you do 26 to the third power times 10 to the third power, in other words, 26 times 26 times 26 times 10 times 10 times 10, you get a very large number. How large? This large. In other words, 17,576,000. Wow, that is quite a lot, 17,576,000. So by choosing 3 uppercase letters and then 3 digits, you have a possibility of choosing 1 out of 17,576,000 different passwords. Oof. Part B. How many passwords are possible if no letter or digit can be repeated and the letters have to be lowercase? Oh, this one's interesting. Now we have a ton of restrictions on this particular password. And again, we're going to take it letters first, then numbers. Now keep in mind what it says. No letter or digit can be repeated. That is crucial information. If we are to get this right, we cannot have a password like AAB or even AAA. Heck, we can't even have a password like CDD because we cannot repeat any letters. And we cannot repeat any digits. So let's think about this logically once again. My first letter, which is going to go right here, in other words, the start of the password, I can choose any of the 26 letters because I know I have not chosen one yet, and so therefore I cannot thus have any repetition just yet. But now once I get to my second letter, I have already chosen one letter from the alphabet. Let's say I chose the letter Q as my first letter in the alphabet, or excuse me, in my password. Therefore, Q is now officially off the table for the second and the third letter because I cannot repeat. I cannot repeat. I cannot repeat. So therefore, if I choose Q as my first letter, then therefore Q is gone from the alphabet for me to use. And therefore, how many letters do I have? For my second letter, only 25. So let's say I choose Q and then I choose, oh, I don't know, E. So now I have a Q and an E. Now 2 letters are gone from the alphabet in order for my third choice to be accurate. And because 2 letters are gone, I don't have 26 anymore. I don't even have 25 anymore. I have 26 minus 2. I have 24 different options. So I have 26 in my first slot, 25 in my second slot, and 24 in my third slot because I cannot repeat. Now this same logic has to be applied to the digits. All right, so now that I'm starting over, for my 6th character must be a digit, I know I have 10 different options to choose from because I can use any of the 10 digits. But once I choose one digit, let's say I choose, I don't know, 5. Now 5's off the table. So how many digits do I have to choose from in my second digit? I only have 9 now. So let's say I choose 5 and then I choose 2. Well, now 5 and 2 are gone. I can't use them again because I can't repeat. So my third digit and final character in my password, I can only have 8 to choose from because I can choose 10 minus 2. I've already used 2 of my numbers, 2 of my digits. So now what I'm multiplying together is 26 times 25 times 24 times 10 times 9 times 8. So those are some very different numbers here. Now again, 26 times 5 times 24. It kept going down because we could not repeat a letter. 10 times 9 times 8. It kept going down because we could not repeat a digit as well. But we do still, of course, have to use the counting principle. So we have to figure out what is 26 times 25 times 24 times 10 times 9 times 8. Well, again, I've done the math for you in the interest of time. This is how many you have. 11,232,000 different passwords to choose from. Now, as you can see, that is kind of a lot, isn't it? But do you notice that it happens to be less than when you have no restrictions whatsoever, which would make perfect sense. Very good. And just as an interesting point, you might want to check out this, the worst passwords of 2013. Yeah, I would say this number 1 password, pretty terrible. And look at the 3rd password, that's horrible. Heck, look at the 6th. Look at the 8th. Interesting. Although I have to admit, the 10th worst password of 2013, I would have never thought to use Adobe 123. I don't even know why the word Adobe came into play there. Maybe because it's the software? Who knows? This is a pretty terrible password too. All ones. I love you as a password? Okay. But this is by far my favorite. The word password as your password. Notice that it was the number 2 worst passwords of 2013. So if you have any of these passwords, I highly suggest you change them. Alright, so that's that. Now let me present to you your problem to solve. Each person that works in a company is given a 5-digit code followed by a letter, either uppercase or lowercase. Keep that in mind. We did talk about that, okay? Remember, 26 letters in the alphabet, but for this problem, are you going to use the number 26? Well, you'll have to decide. Each person that works at a company is given a 5-digit code followed by a letter, which means how many characters in total are going to be in the code. These employees must enter their codes on a keypad to enter and exit the office building. The company has 130 employees. That's a lot. What is the probability of someone entering a code at random and gaining entry to the building? So we have to also apply this to probability. Now remember, probability, in this case, in this case, theoretical probability, because we can technically list out all the outcomes. It would be a very large list, but nevertheless, it would be there. Would be how many favorable outcomes out of all possible outcomes. And that's the first thing you want to calculate. is how many possible outcomes there are. In other words, how many different 5-digit code followed by a letter, either uppercase or lowercase, passwords are available. And then what's the probability of just some random person entering a code at random and gaining entry into the building? So you're going to have to combine techniques, and you will definitely have to use the counting principle to figure out which part is going to be used in your probability. All right. Feel free to contact me should you have any questions. Good luck. Oh, but wait, I have not gone anywhere just yet. Congratulations to you for not stopping the video just because I said good luck. And to reward you, here you have a second opportunity for a bonus point on this particular screencast response if you answer the following question accurately. So again, just because I said, all right, good luck, and contact me if you have any questions, you didn't stop the video. You kept going. And you saw, hey, there's still more here. I wonder what he has to say. Well, here's what I have to say. This question right here is a bonus question. If you answer this correctly, you get an extra bonus point on this particular screencast. Here's the question. It's a little bit more challenging. You flip a coin 5 times. What is the probability that the results are all heads or all tails? Again, you will need the counting principle for this one, and you will also need probability, of course. All right, nice job. Good luck.